has been globally supported by medical literature. There's an increase in knee stiffness as age increases. Now, the current problem solution for this utilizes passive motion therapy. And what passive motion therapy does is it flexes and extends your leg about your knee to increase lower body circulation as well as promote long-term tissue regrowth. Additionally, studies have also found that patients above the age of 64 spend around 6 to 9 hours a day participating in sedentary activities. This may include watching TV or sitting down for long periods of time. Now, what our team proposes is a device that would bring passive motion therapy into the comfort of the user's home with a number of programmable features. The overall system architecture of the passive motion chair comprises of 2 microcontrollers, a Raspberry Pi and an Arduino Mega, 2 linear actuators, and 2 load cells. The Raspberry Pi and Arduino are connected via I2C connection, necessary for them to communicate in the same logic voltage.
To adjust for a variety of heights, we designed a modular system to fit under the prefabricated armchair. A side-mounted actuator on the C-angle subframe pushes the extension axis on the carriage system to the back of the user's knee, and a second actuator creates the main function of the passive motion chair. We selected steel angle stock due to its affordability, availability, and ease of manufacturing.
Besides being able to create users with predefined parameters, the user also has the ability to set the device in manual mode, which allows them to flex or extend their leg to a certain point that they wish. For example, if I want to extend, I'll just let it go until a point I would like to stop. And from here, I can also flex until any point in time. Also, while in manual mode, the user can interrupt the movement by increasing or decreasing the height adjustment. And once they press stop, the previous movement continues.
Okay, so if a user want to create a profile, they go here, they click on the plus sign, they click on the name, and they can type their name, go to the speed, set up the speed for it, go to flexion, set up your flexion. Let's say if they want to do 40, same 40, max cycle 70, submit, and then they can use the profile they created.
The 2 load cells are placed in the leg rest, and they continuously monitor the current angle, which is logged and stored into the Raspberry Pi's micro SD card. Now, this is beneficial for long-term assessment of the effectiveness of the passive motion chair. It continuously reads force applied on the leg. If it detects a large increase based on calibration threshold, the device will stop. An added feature of the passive motion chair includes being able to control the screen with an external controller. This is useful for scenarios in which the patient cannot control the system themselves, or their caretaker has, or as well as a medical professional has to assist them in such. For example, from here, I can allow my patients to take on Max S profile, as well as control every single functionality on the screen. For example, I can stop the movement, or I can also go into manual mode, flex, as well as change the height adjustment of the patient.
If this device was mass produced, it would allow us to buy materials in bulk and decrease the cost of production. This would also allow us to decrease the retail price and possibly increase the profit margin.
In conclusion, we look at the future directions we can take with our products. With better actuators, we can minimize the noise. Our second issue was with the height adjustments. I am above 6 feet and my legs are barely getting off the ground. So optimizing the design approach, we can be able to fix that and be able to get a better solution for people above 6 feet. The next problem is the issue of the weight. If we can optimize the design materials used, we can reduce the stress on the users when they have to move the chair from one point to another.